Okay, good afternoon. More or less this slide summarizes what we discussed the last time. And today the idea is to go a bit more into the details of all those main components of the information retrieval system. So again, we have a number of documents, the collection of documents that have to be indexed in order to answer to a given query that actually represents the needs, the information need of your user. And so the first step is to tokenize such collection of documents. What is the tokenization? Basically is extracting from the sentences in the documents unit of lexical elements, we will see later on. And then we have some linguistic modules. In this example, the simplest one. Basically, we go from capital letters to small letters. And finally, we build the index as the final step, as we saw last time. Okay? So the idea today is to go a bit more into the details and all the the details of those components, and we will show also the first, code in a library named NLTK. It's one example, and in the next classes we will also see Lucene, which is actually a library which allows you to build quite complex and state-of-the-art information retrieval system. Okay, so we have those documents in input. Now we need to answer a number of questions. So first of all, what is the format of the collection of documents? As we said last time, we have basically documents that are text, but as you know, probably text can be PDF, can be HTML, can be Excel, can be whatever you want. So the first question we need to answer to some extent is what kind of format is in the document. Second, what is the language of this document? Okay? And we will see later on that this language can make a lot of differences in the processing of the documents. And finally, what character set has been used in order to encode the document. All those questions, all those main points that we have to consider can be seen as classification problems. Okay, so in the next lectures we will see what is exactly a classification problem. But now, just to give you a rough example, just to understand what we are talking about. Okay, in general, it's a classification problem, but can be solved heuristically. What is an heuristic? Is something that is an easy set of rules that you apply in order to have an approximate solution to the problem. Okay? But in general, those are classification problems. In classification problem, you have a number of points in a feature space. So as an example, those are can be documents, and you have the green documents and the blue documents, and what you want to find out is a region which allows you to determine whether a new documents that will appear, in this particular point, example, the question mark, will be either classified as a blue document or as a green document. Okay? This region can be a linear region, or can be something more complex. And we will see, depending on whether we have a linear boundary rather than something more complex, we have to apply different classification algorithms. Okay? So why the problem we saw before can be thought as classification problems? Because, okay, maybe those are PDF documents and those are HTML documents. Those are English documents, and those are Italian documents, and those are documents encoded in UTF whatever, and those are encoded in another kind of encoding. Okay? So anytime we see a new document, a question mark, we have to answer to those questions, solving a suitable classification problem. Okay, just a quick reminder, what is the character encoding? Is the way through which you basically encode characters in the documents, right? And so as you see, as an example, those are different characters. And in UTF, those characters are sorted. Okay, so the number 41 is the A, capital A. The number 5D0 is this symbol. Actually, I don't know what symbol is it. Anyway, all the symbols have a different point in the list of all the possible symbols. And then, depending on the type of encoding, UTF-8, 16, or 32, in this particular case, you encode it in a different way. Okay, so the encoding is the way through which you pass from symbols into the documents to bytes that represent that symbol into the document. Okay. Now, clearly, in the ideal world, all the documents have a unique format, a unique language, and so on and so forth. But actually, in the real world, you have a number of difficulties. So as an example, you might have documents containing different languages, and thus the index must contain terms from different languages. You can have, as an example, French mail with German PDF attachment, not only inside the same document, but all the components of the documents. If you think about an email and the attachment, you can have an email which is, as an example, in this example, in French, and there's a number of PDF attachment, or English language contract, and so on and so forth. You can imagine, right? In general, in order to deal with all those complexities, you have a suitable either commercial or open source library which allows you to tackle with all those issues. Furthermore, we want to, if you remind the general architecture we are considering, collection of documents, a query gives you a number of documents that are relevant for that query. But what is the grain size? Namely, is it a single file, a single document? Is it an email maybe with a number of attachments? Is it maybe a group of files? And so on and so forth, okay? This simple introduction just to give you a rough idea of the complexity of the information retrieval task. Okay, but anyway, in the picture we saw from the collection, the first step is to identify token. So what is named tokenization. Let's see. So the input is the document. In this very simple case, the document is friends, romance, and countrymen. And what we want as output is a list of tokens. In this particular case, it's probably pretty simple, friends, romance, and countrymen. Usually, what is, in your opinion, the simplest strategy in order to identify tokens? White spaces, right? It can be either white spaces, maybe it can be commas, stuff like that. Okay, indeed, this is the simplest strategy. Okay, but first of all, let's understand what is a token. A token is an instance of a sequence of characters that are grouped together as a useful semantic unit for processing. So while your intuition is pretty right, I mean, usually we use white spaces in order to have the first tokenization, but nobody, I mean, we can also consider a completely different tokenization. As an example, France is one of the token, and romance and countryman could be another one. It depends on the semantic that you have in mind. Okay. Indeed, the main question we need to answer is that those tokens are the candidate to become an entry in the index. Do you remember from token we will get terms, and keep always in mind that at the end we want to build an inverted index that basically is made of terms. Frequency, do you remind why we need frequencies?
The number of the token.
Because, give me an example. Why do we need frequencies? We saw it last time. Optimizing the query. As an example, if we have an OR query, we can guess the number of terms in the query looking at the frequency, right? And so then we remember that if we have an end of difference of different terms, it's better to start with the smallest one in order to reduce the complexity of the whole query. So the frequency helps us, in case we have OR, to have a rough estimation of the length of the term. Okay, good. So again, keep in mind that we want to build this index. It's made of terms. So now we are looking for terms, frequencies, and then the posting list, right? The documents that contain that term. Good. Okay, now just to give again you an idea of what kind of complexity we have, the main question we want to answer, what are valid tokens to emit? Again, the simplest strategy is easy, white spaces, but just to give you an example, what is the tokenization for the Finland's capital? It can be Finland and S, or Finland's, or Finland's, or if you have hyphenation, Hewlett-Packard, okay? Okay, it can be either a single token, Hewlett-Packard, because most of the time usually we refer to Hewlett-Packard as Hewlett-Packard together, or Hewlett and Packard. And just to give you another example, maybe, okay, state of the art can be state of the art altogether, or can be state of the art. But if I give you coeducation and lowercase, okay, also consider that for most of us, it's difficult to grasp everything because usually you should be very proficient with the language you are considering, right? While we are talking about English, but most of us are Italians, so maybe we didn't get all the language complexity behind. But anyway, coeducation, would you split the terms in co and education, or would you put together coeducation? Roughly, I do believe it sounds for you familiar that coeducation is a single term, right? Well, this is not the case for lowercase. It could be lowercase. It's more natural, okay? Okay, now, as an example, San Francisco. Is it San Francisco or San and Francisco? So you can now grasp what is the complexity of tokenization. That is supposed to be a quite simple task. You say, as you said, okay, I will take white spaces in order to identify tokens. But again, this example makes clear some of the difficulties. Then, again, in terms of dates, please keep always in mind that what we want is that if two tokens are semantically related, namely they are describing the same thing, we would in principle use the same term for the token. Okay? So here you have two examples, 3/20/91, which is a concise version of a date, or the extended one, March 12, 1991, 20/3/91. Basically, we are referring to the same date, so we would have the same term, but are completely different. And so on and so forth. 55 BC. Is BC a single term, or we have to split in before Christ, or do we have B and C, and so on and so forth? B52. Okay, so you see, there are a number of really complex, simple, I would say trivial problems, but a lot of them with a number of cases. And in order to make the difference in terms of efficiency and more in terms of effectiveness of the information retrieval task, you have to consider all those problems very carefully. Okay? Often you can index metadata. What is a metadata? It's a data describing the data outside the index in order to reinforce some of the properties that we want to consider. Okay? Good. Then we have tokenization issues that are related specifically to the language. Again, unfortunately, I don't know French, but the example is very clear, and it's even more clear, the sentence here. So do we have to consider l'ensemble, one token or two? A single token l'ensemble or two token L and the ensemble. Now, as an example, we want that l'ensemble should match with an ensemble. But as you see here, apparently, up to 2003, Google was not able to make this happen. Okay. And in general, we have the issue about internationalization. Now, we always assume that our information retrieval system will work for all the languages. But now it should be clear for you what are the complexities of all those languages. And even more importantly, the main problem is that you need to know deeply the language in order to design a suitable solution. Okay? Another example. In German, known compounds are not segmented. Okay? So this is a perfectly okay German sentence. Okay? The fact is that, so the translation is life insurance company employee. Now you can consider it again as a single token, but if you allow to split this single token using compound splitter, you can improve the performance by 15%. Okay? Yeah.
When we say improving the performance here, what performance are we getting?
Okay, up to now we know only the performance in terms of precision and recall. We will see later on that there are other metrics. But now think, for the moment, it's okay to say that we will improve the performance of precision and recall. Not only, actually. When we talk about the performance, we will see later on, we can improve also the performance in terms of time that we need in order to answer to a given query. But here the answer is precision and recall mostly. Okay? Okay, again, I could have difficulties with English. I don't know anything about English, German, and French, but I have to confess that Chinese and Japanese, it's even more complex to me. So just to mention that clearly, if you go to a language that is by far more distant from your culture, this becomes even more difficult. Okay? And so again, simply considering the dates or amounts, apparently, in Chinese and the Japanese, you have different formats for, namely, you can describe the same date or the same amount in completely different formats. Or as an example, if you consider Arabic or Hebrew, usually are languages that are written from the right to the left, except for the dates that are actually from the left to the right. Again, you can imagine how internationalization is a big issue. The good news here is that there are very effective libraries that works pretty well with a number of languages. Even if I guess now it's extremely timing what is called the voice recognition and technologies, right? Okay, I don't know whether you have any experience about the voice recognition technology, but the quality of the recognition of English or German or French are much better than Italian and other languages. There is clearly an incremental knowledge, but usually they prefer to reach good performances on the languages that are widespread around the world, namely English and Spanish before, and then all the others. And you can experience it in particular if you do some experiments with open source tools for voice recognition techniques, for voice recognition tools. That works pretty well, again, with English and not so well for Italian. This is because you have to invest a lot in order to build an information retrieval system that takes into the proper consideration all those issues that we have mentioned, simply mentioned up to now. Okay, now, assuming that we have a good tokenization system, namely from the sentences into the documents we can extract tokens, the next step is to remove from this token list what are called stop words. Namely, those stop words are the most common words in a dictionary that usually have a very little semantics. I mean, the article, conjunction, and stuff like that usually are not very, they do not provide a lot of information. And they are a lot. A significant fraction of the whole dictionary could be made of those words if you do not remove them. So, at least in principle, we have to think about how to remove those stop words in order to improve the performance of our system. Now, it's important that you keep in mind that information retrieval is the base of web searching, okay? And actually, information retrieval has been developed on collection of documents even before the advent of web searching. Anyway, if we consider web searching, we're talking about something that has now, say, roughly 20 years now, more or less. Okay? Even more, actually, but let's assume 20 years. Oh, now, if you go back 20 years from now, all the hardware that you had available was extremely resource constrained with respect to the ones that you have now. So problems that were extremely important 20 years ago, maybe now are less important. Among the important problems of 20 years ago was the fact that memory was very few, I mean RAM memory. Hard disks were very limited, and also CPU, with respect to what we have nowadays. Thus, the reduction of space, removing stop words, was a real issue. We will see later on that actually nowadays is less relevant than before. But please keep in mind that all those techniques have been developed 20 or 30 years ago, when the development of efficient solution in the use of CPU, RAM, and disk were extremely important. And we will see actually that those are still very important. Even because you can imagine that the next frontier is moving from text to audio, and from audio to video, and from video to high definition video. And so all these problems becomes, again, in terms of kind of problems, again, very relevant, because the size of video is extremely, it's huge, okay? So anyway, you have a problem of effectiveness and efficiency. Indeed, the trend is a way of doing this. We will see later on that thanks to good compression techniques, actually, the occupancy of the stop words is not actually dramatic. And furthermore, thanks to good query optimization technique, actually, the increase in time due to the fact that you consider stop words in terms of time to answer to a given query is not so high. Okay? So we will see that compression will reduce the space needed to store all the stop words, and optimization allows us anyway to do not pay a lot when we consider the stop words into the query. And at the same time, in some cases, stop words are needed. The King of Denmark, or Let It Be, or To Be or Not to Be, actually, if you remove the stop words, it's extremely difficult to get good results for such kind of query. Or even more importantly, if we want a relational query, okay, to can be considered a stop word, but clearly flights to London, here, if you remove the to, it's extremely difficult to understand what we are looking for, right? Okay. Now, the next step, we have token, we have removed the stop words. Now we need again to normalize the token. One of the examples, if you have USA, probably you want, what is the normalization? The normalization is the operation in order to have the same representation for tokens that actually are the same thing. So USA with punctuation and without are actually USA. Okay? So you want to put together the stuff. And now, a term is a normalized word type, which is an entry in our higher system dictionary. Okay? So finally, after the normalization, we have the term that are the entries in our dictionary. Okay. Usually we can define equivalence like in this case USA and use again USA with the point or without is USA, and then you can say that you can write down equivalence classes in which anti-discriminatory and anti-discriminatory will be mapped both in anti-discriminatory without the hyphenation and so on and so forth. Okay. In the languages, you have the problem with accent, but let's make a simple experiment. When you make a Google query, do you use accent or not? In Italian, I mean, clearly. Most of the time, I don't. Or maybe I will, but it's not actually something that I will always use. Okay? So are we using resume with or without accent? Or here you have the two versions of Tübingen that should be equivalent. Again, in all those cases, what you have to consider always is what would be the behavior of your users. Okay, so you have to think about improving the user experience. You can think about a very effective system, but if you are asking to your user to behave in a way that is not consistent with their common behavior, maybe it would not work. So try to adapt your system to the user habits in order to provide them the most satisfactory user experience. Okay? Namely, the most important question is how are your users like to write their queries for the words? That's it. Once you understand it, you can map it into the best way in order to normalize the queries. Okay. Again, there are a number of problems for the, we already said for the dates, or in this example, this myth here, which is a capital myth, is it the Massachusetts Institute of Technology or is it myth in German? Okay? So we need a way to normalize entries that must be indexed with the same terms. Another example is case folding. So in general, you can reduce everything to lowercase. But again, here there is a very interesting example. So in this example, you have fed, sale, and the example is this, again, a Google example. If you query CAT, which usually is the acronym for Caterpillar, actually in Google up to 2011 or something like that, you got lollycats, so the animals. So again, the way in which you normalize is extremely important. Another example you can think about is window. If you put window usually in any, I made an experiment today. If you write window, you get almost all results about window operating system. Okay? You have to put window furniture or window something else in order to get the windows actually to look outside. But here you can think about different mapping, right? If you write it with a small w, probably you are considering the furniture. If you write DS, maybe you are both the furniture or the operating system. But if you write it capital, in this case, it's definitely the operating system because you have in mind the operating system. So you can map those classes into distinct normalization classes. Okay? In general, this is very, this is potentially more powerful, but in general is less efficient. Okay? Finally, we could map into the same term tokens that apparently have nothing to share in terms of syntax. Okay, as an example, you can say that car and automobile are the same stuff. And indeed, in terms of the query, are the same stuff. But clearly, you have to tell it to the system and to create this equivalent class. So what you can do when you get a query, you can basically map the original query into terms that are in your dictionary and are considered equivalent according to your mapping. This is the step that you have to perform. And finally, what about spelling mistakes? Namely, up to now, our assumption was that everybody is performing as expected. So everybody is writing exactly what you want to search for. But actually, we do a lot of it, at least I do a lot of errors, misspelling and stuff like that. And now we have to think about how to deal with those misspellings. Okay? Okay. Now, questions up to now? So I know this long list of all the possible problems is not very exciting, but it's extremely important that, and again, you can solve it easily employing standard libraries or tools. So it is not something usually that you have to implement unless you will actually work into the details of the implementation of information retrieval system. But it's extremely important that you understand all the complexity behind those systems. Okay? So that's the purpose of this lecture mainly. Okay, next. Lemmatization, what is the idea behind the lemmatization is that you want to reduce the variance with respect to a base form of a given term. So, as an example, if you have ham, are, is, the lemmatization can map all those terms into B, like car, cars, or whatever you see here is mapped into car. Okay. So, an example of lemmatization is the boy's car are different colors, is mapped into the boy car, B different color. Why is this an advantage? Because it allows you to reduce the number of terms and in a way maintain the semantic of the original phrase, except in some cases related to the time when happened this stuff in this particular case. Okay. Okay, again, what we can do is to reduce the term to their roots before indexing by lemmatization. And then we have stemming, which allows you, and is language dependent, again to remove all the parts of our tokens that are not of interest. So in this case, automates, automatic, automation have all the same root, which is automat. Okay? And so in this particular example, for example, compressed and compression are both accepted as equivalent to compress, will be mapped through to stemming. For example, compress and compress are both accepted as equivalent to compress. Okay? Because we have basically reduced all the forms to their root forms. Okay, how can we do stemming? What kind of algorithm can be used? And one of the possibilities is to use the Porter algorithm. It's actually one of the most common used in English. And what is interesting is, despite the fact that it's relatively simple, it performs pretty well. It is at least as good as other stemming algorithms. Okay, it's made of a number of passes, a number of rules that are applied one after the other. You apply those phases one after the other sequentially. In each phase, you have a set of commands. We will see an example later on. In general, the convention is, whenever possible, apply the rules that can be applied to the longest suffix, okay, in order to reduce as quick as possible. Example of rules. As an example, if you have S's, you map it to SS. If you have yes, you map it to Y, and so on and so forth. Rational to 8, rational to tion, and those are the kind of rules that you will apply. And then you might have sensitive rules. In this particular case, replacement will be mapped into replace, and so on and so forth. But again, we don't want to go into the details of that. We will see later in the example I show you on LTK how simple it is to apply the stemmer, the Porter stemmer. Okay. There are clearly other stemmers. As an example, in NLTK, the library we will see later on, you can apply easily snowball, and many other. You have a number of library. This is an example of what you can get with different stemmer. As you can see, basically, you are not changing too much the original text. In some cases, I don't know. Here you have analysis, which is mapped in the Levin's. In Porter's is analysis, while in Pace is analysis, and so on and so forth. But basically, the structure should be now clear. The idea is to reduce to the root. Depending on what kind of stemmer you use, you have different results. Clearly, you have to use the same stemmer for all the documents in your collection. Okay. Now, what you have to consider is that not only the transformation of the stemmer are language specific, because clearly you cannot apply Porter to Italian, even if you see the rules, even if we saw very quickly the rules, should be pretty clear that those rules have been conceived for English language. But not only are language specific, but also application specific, because maybe they depend on the context of the application you are, or the information retrieval system you are designing. We saw Westlaw as an information retrieval system for documents, a corpus of documents related to the laws. Clearly, maybe in that specific case, some very peculiar transformation rules must be applied in order to improve the performance of the system. Okay? Usually, you have to consider those stemmers as a plugin that you put in the pipeline. The pipeline is tokenization. Among the pipeline, we saw tokenization, normalization, and now we have the language-specific part in which you can put in the pipeline different blocks according to your needs. Okay? And again, both open source and commercial plugins are available. Now, let me show very quickly the example I told you before. And then we'll go back to the slides. I don't see the mouse. Where is it? Here. First step is tokenization, we saw. Now, this is an example of a Python library named NLTK. As usually, from the NLTK, you import the tokenizer. In this particular case, we can have, as an example, two kinds of tokenizer, a word tokenizer and a sentence tokenizer. Okay? Let's see what happens when we run it on the sentence that you see on the top. So, terminal. Okay, I use pipenv in order to have virtual environments in Python. So this is the virtual environments in which I installed all the NLTK library, and it's very simple. Pip install NLTK. That's it. In this example, we can run Python. What's the name? My underscore Okay, and you see that, as expected, the word tokenizer takes all the words basically using the white spaces, as we said before, as the separator for the tokens. While the sentence tokenizer does exactly the following. Instead of taking a single word, they use as a token a sentence. And in this case, the separator for the sentence is the full stop at the end of the sentences. Okay? So this is the first block, tokenizer. The second block is the stop words. And again, it's, as you see, it's very simple. First, we have to define the set of stop words. And being a language specific, you have to say stop words set, stop words English. Clearly, depending on the language you are considering, you will change English, Italian, French, whatever it is. Then you apply the tokenizer we saw before in order to get the words. And in order to filter it, you pass by all the list, all the words, and you remove the sentences, the terms that are in the stop word. Okay? Here you are iterating over all the words obtained by the tokenizer, and simply you remove, actually you append in the filtered part all the words that are not in the stop words. So if you print both this stuff, so in this particular case is Python my stop word. Okay, you see that the list, the two lists are different. And in particular, what you have removed is and as a stop word, which is present in the original list and has been removed in the stop, thanks to the stop words, no, and so on and so forth. Okay? So as you see, it's very simple. Finally, let's see the stemmer. Okay. We have a set of plurals in this case, just to make an experiment with the stemming. We use the Porter stemmer. And simple, what we do, we pass all the terms to the stemmer. That, as we see, one of the goals is to put to transform the plurals into singles. Okay? And so again, just to see it, is my not only, as an example, caresses, here is caress, flies is fly, and so on and so forth. Okay? Now, message, you can do everything with the library. And now I will show you, before the stop, for the first stop, I will show you how to put all together in order to get a very simple inverted index. So a very basic, trivial information retrieval system. Okay? So we can put all together here in the, where is it? Okay, again, I define a class index. In this class index, as you see, I have a tokenizer and the stemmer. I use in this particular case a dictionary. We will see later on what are the alternatives in order to build the index, but please keep in mind that basically I have two main data structures. One are dictionaries, in which I have a key, which allows me to access in constant time entries in the dictionary, and the other one are binary tree or B trees, even better. Okay? And then all the entries in this dictionary is a list of documents, because I remind you that the idea is the following. Here we have the terms. Here we have possibly the frequencies, even if we don't use it. And here the list of documents. So the key are the terms, which are the key to access the dictionary. And the list is the list of documents. Okay. Okay. I have basically two operations possible. One is the lookup. What does the lookup? Allows you to access the entry in the dictionary indexed by the word that you provide in input. Okay, what you do is the following. You transform the word in lower letters, and then you apply the stemmer, even to the query clearly, because you want the same root. Okay, so you apply the. Notice that this lookup is basically the way through which you make the query. So you apply the stemmer, and then you simply access the document into the index that is pointed by the key is the list of documents, which the key is the index that you get as input. Or you can add a document. In order to add the document, you apply exactly all the passes, all the phases we saw before. So first, we take the document in input, and we get all the documents. Sorry, all the tokens. Okay? So we remove the stop words. Okay? We apply the stemmer, as we saw before. And finally, we add the element, the document, in the proper index. Okay? So we basically construct this part. Does it make sense? Now, a very simple example. This is an example I took from a web page. You have the reference at the beginning of this code. I will share on Piazza at the end of the class. Now, what you do is the following. You build the index simply passing the instances, the references to the tokenizer that you want to use, the word tokenizer we saw before, to the stemmer you want to use. In this case, it's not exactly Porter, but it's this English stemmer, and to the stop words you want to use. Okay? Because I remind you, those are the elements that are initialized when you call the constructor of this class. And finally, what can you do? Simply you add documents. And as an example, you can make the following query. Index lookup lobs, and gives you back all the documents that contain lobs, in this particular case, in the root form, right? So that's why we get tunnel of love, wallalot love, since I've been loving you. You see, love allows you to get documents containing loving. Lobs, excuse me, allows you to get documents containing loving or love, both of them. Okay? Okay. what I think it's nice is that even if this is a very simple example, actually shows you all the main ingredients we saw up to now, and you can play with it easily. Okay. Questions?
Will this be uploaded?
Sure. Sure. I'll put it on Piazza later on. Okay, the code is actually not already on Piazza, but I'll put it later on. Consider that the slides are, we are basically annotating the slides of the Stanford group. So if you want to have a look at what will be discussed, at least for the next, at least up to the classification, we will follow those slides. Even if likely we will not go into some details of those slides because we want to move towards something more specific for web information retrieval. But you have a clear idea of what is the path we will follow. Questions? Okay, 10 minutes of break and then we'll start again. Okay.